We often ask ourselves, what is the probability of life? Not even intelligent, just simple living organisms. We can't know the exact number, but we can say it is very, very rare. You might ask, like how rare? Well, you be the judge. If we look at the structure of our universe, we see an elegant structure built from atoms, protons, electrons, gravity, the electromagnetic force, nuclear fusion, and much more. Each of these components has precise, unchanging values known as physical constants that govern how the universe operates. These include the strength of gravity, the mass of elementary particles, the speed of light, and the strength of fundamental forces. But if any one of these values were even slightly different, the universe as we know it simply wouldn't exist. I'm not even talking only about life, but matter, stars, or even atoms themselves. Gravity. It's the weakest of the four fundamental forces, but its weakness is exactly what makes the universe stable. If gravity were only slightly stronger, say stronger by 1 part in 10 to the power of 36, the universe would have collapsed in on itself shortly after the Big Bang, long before stars and galaxies could form. If it were weaker by the same margin, the expansion of the universe would have accelerated too quickly, and matter would never have clumped together to form structures. The formation of galaxies, stars, and planets, all of it, depends on gravity being precisely what it is. Now consider the electromagnetic force, which governs the interaction between charged particles. It is very, very important thing in chemistry and biology because it holds atoms and molecules together. The strength of this force is described by a number called the fine structure constant, approximately 1/137th. If this value were slightly larger, let's say 1/136, atoms wouldn't hold together, electrons would spiral into the nucleus. If it were slightly smaller, electrons wouldn't bind at all and atoms would fly apart. In either case, your body, your brain, food, cars, literally everything you see around you wouldn't exist because it couldn't. Well, very fine-tuned physics doesn't end here. The strong nuclear force is another example. It holds protons and neutrons together in the atomic nucleus. If this force were just 2% weaker, the only stable element in the universe would be hydrogen. No heavier elements like carbon, oxygen, or iron could exist. On the other hand, if it were 0.5% stronger, hydrogen, the simplest and most abundant element in the universe, wouldn't form at all during the early universe. Then there's the triple alpha process, a nuclear reaction inside stars responsible for creating carbon. In order for this process to occur, 3 helium nuclei, alpha particles, must collide under extreme conditions to form carbon. This reaction relies on a very specific resonance in the carbon-12 nucleus, a kind of energy sweet spot. If this resonance level were just 0.05% different, the reaction wouldn't work efficiently, and carbon wouldn't form in the quantities needed for life. The odds of such a narrow energy window existing purely by chance are incredibly low, yet it exists. And it doesn't end with carbon. The ratio of the electron mass to the proton mass is another fixed value that must fall within a narrow range. So is the strength of the weak nuclear force, which governs radioactive decay and plays a crucial role in how stars burn their fuel. Even the cosmological constant, a term in Einstein's equations that describes the energy density of empty space, must be fine-tuned to a degree that's almost impossible to comprehend. If it were just slightly higher, the universe would have expanded too rapidly for galaxies to form. If it were lower, the universe could have collapsed long ago. The required precision is 1 part in 10 to the power of 120, a number with 120 zeros. What all this points to is a universe balanced on a knife's edge. The fundamental constants of nature are so narrow, so precise, that even the slightest change would make our existence impossible. I am not trying to say that the universe was deliberately designed, but that it appears to be calibrated for the emergence of complexity in life. There are a few possible explanations for this. One is the anthropic principle. We observe the universe to be life-permitting because we're here to observe it. In other words, we could exist in the universe only if these conditions are followed. Another explanation is the multiverse hypothesis, The idea that our universe is just one of countless others, each with different physical laws and constants. Most would be sterile and lifeless, but ours just happens to have the right conditions. Whether this fine-tuning is the result of chance, necessity, or something deeper remains one of the greatest mysteries in science. But what's clear is that everything we know, every galaxy, every atom, every living thing, rests on an incredibly fragile foundation. A foundation that, against overwhelming odds, holds steady. Okay, let's say you have right mass of proton and the right gravitational force and etc. But that's unfortunately still not enough to have us. At the very beginning, the universe should have been absolutely empty. According to the laws of physics, the Big Bang created equal amounts of matter and antimatter. And when matter and antimatter meet, they annihilate completely, leaving behind only energy. So logically, the instant the universe began, every particle of matter should have been canceled out by its antimatter counterpart. No atoms, no stars, no galaxies, no Earth, no life. And yet, here we are. The reason? At some point in the earliest moments of time, just millionths of a second after the Big Bang, there was a tiny imbalance. For you to understand the proportion, for every 10 billion particles of antimatter, there were 10 billion and 1 particles of matter. That single extra particle in every 10 billion is the reason anything exists at all. Everything you see, your body, the planet, every star in the sky, is made from the leftover matter that didn't get destroyed. This difference is unimaginably small. A 0.000000001% imbalance. But without it, the entire universe would be filled with nothing but radiation. Light without substance. No elements. Nothing. Scientists call this phenomenon baryon asymmetry, and it remains one of the great unanswered questions in physics. The Standard Model, the best theory we have for how particles behave, predicts that matter and antimatter should have been created in exactly equal amounts. Yet something tipped the balance. We know that, under very rare conditions, some particles behave slightly differently than their antiparticles. This is known as CP violation, a subtle asymmetry in the way certain particles decay. But the CP violation we've observed so far isn't nearly enough to explain the vast imbalance that led to a matter-filled universe. In other words, our very existence points to some hidden mechanism in the early universe, something we haven't discovered yet. Something that nudged the cosmic scales ever so slightly in favor of matter over antimatter. And think about the consequences of that 1 in 10 billion chance. If the numbers had come out even a fraction more balanced, we wouldn't be having this conversation. There wouldn't even be space for the conversation to happen in. There would be no structure, no complexity, no time as we experience it. Just cold, sterile light streaming endlessly through empty space. A single particle in every 10 billion made the difference between nothing and everything. And guess what? That is still not enough to life to exist. When we imagine the early universe, we might think of something grand and vast, but in truth, it was simple. Hydrogen, helium, a tiny trace of lithium. That was it. None of the elements that make up planets, oceans, or living cells. The periodic table, as we know, it didn't exist. But over time, something extraordinary happened. The universe built the ingredients for life inside the hearts of stars. At first, the universe was just a soup of subatomic particles. But as it cooled, those particles came together to form atoms, mostly hydrogen, with some helium. These gases gathered under the force of gravity, forming the first stars. And inside those stars, nuclear fusion began. Hydrogen atoms were smashed together under immense pressure and temperature, creating helium and releasing energy. This is what makes stars shine. But fusion doesn't stop at helium. In larger stars, the pressure becomes high enough to fuse helium into heavier elements: carbon, oxygen, neon, magnesium, and eventually iron. Each of these reactions releases energy, helping the star maintain its balance against gravitational collapse. These elements, the building blocks of planets and life, were not present at the beginning. They were forged, atom by atom, inside stellar furnaces. Yet even stars have their limits. Iron marks the point where fusion no longer produces energy. When a massive star's core fills with iron, it can no longer support itself. Gravity wins. The core collapses and the star explodes in a supernova, a single event that releases more energy in a few seconds than our sun will emit in its entire lifetime, or, if star is too heavy after its death, a pure black hole. And this very process is the next step to life, to us. The supernova explosion provides the energy needed to create even heavier elements: gold, uranium, lead. In that brief, catastrophic moment, the periodic table is completed. But just as importantly, those elements don't stay trapped in the wreckage. They're scattered across space, seeding the next generation of stars, planets, and eventually, life. The atoms in your bones, your blood, your brain, they were once inside the core of a dying star. Every element heavier than hydrogen was made in a stellar furnace or born in an explosion powerful enough to reshape galaxies. This was the next one in a billion step. Stars didn't just provide warmth or light. They performed a kind of cosmic alchemy, transforming a lifeless universe into one filled with potential. But it depended on the laws of physics being just right. The balance of gravity and fusion, the stability of certain atomic nuclei, the ability of exploding stars to eject their contents into space. Without stars living and dying in precisely the way they do, there would be no carbon-based life, no Earth, no biology, no us. In the chaos following generations of supernova, enormous clouds of gas and dust filled the galaxy. These clouds, enriched with the elements created in stars, began to collapse under gravity, forming new stars. Around many of these young stars, leftover material formed rotating disks. From those disks, planets began to emerge. But not all planets are created equal. Some grow too large, becoming gas giants like Jupiter or Saturn. Others are too small, like Mercury or the Moon, unable to hold onto an atmosphere. Earth somehow formed in the middle ground, not too big, not too small, just the right size to sustain life. This alone is rare. Earth's mass, about 5.97 times 10 to the power of 24 kilograms, means it has enough gravity to retain a thick, protective atmosphere, but not so much that the pressure on the surface becomes extreme. That atmosphere helps trap heat, allows liquid water to exist, and protects life from harmful radiation. But again, it's not just about size. Earth is also made of the right stuff. Our planet has a metal-rich core, primarily iron and nickel. This is no accident. It's the result of countless collisions and a long history of planetary differentiation, where heavier elements sank to the center and lighter ones rose to the surface. That metallic core does something extraordinary. It spins, and as it spins, it generates a magnetic field. This magnetic field acts like a giant shield, deflecting solar wind, streams of charged particles constantly emitted by the sun. Without it, the solar wind would slowly strip away our atmosphere, as it did on Mars. Earth's magnetic field also helps prevent radiation from bombarding the surface, making complex life not just possible, but sustainable. And then there's Earth's position in the solar system. Not only is it in the habitable zone, the narrow band where temperatures allow liquid water to exist, but it's also in a relatively stable orbit, thanks in part to the gravitational influence of the Moon and nearby planets. A more elliptical orbit would lead to wild temperature swings. A slightly different distance from the Sun, and water could freeze solid or boil away. In short, Earth had to thread the needle. It had to form at just the right distance from a stable star with the just right amount of mass and the right internal structure. It needed metals. It needed a magnetic field. It needed to hold an atmosphere. If you're watching this video at night and you have clear sky, you should right now open window, look at moon, and say thank you. Before you will call me an idiot, let me say what she did to us. Only a few people realize how deeply it shaped the conditions that allowed life to thrive on Earth. And even fewer know just how unlikely its existence truly is. Roughly 4.5 billion years ago, in the chaotic early days of the solar system, Earth was still forming. It was young, molten, and unstable. Then, a planetary body roughly the size of Mars, at the speed of 25,000 kilometers per hour, collided with the proto-Earth in a violent, catastrophic impact. This object is often referred to as Theia, though no trace of it remains today. The collision was unimaginably intense. Debris from Earth and Theia was ejected into orbit, forming a glowing disk of molten rock and vapor circling the young planet. Over time, this material combined. Gravity pulled it together, piece by piece, until it formed what would become our moon. But here's the crucial part. The impact didn't destroy Earth. It didn't blast our planet apart or send it careening into a different orbit. Somehow, the energy was just right, enough to create the moon, but not enough to end the story before it even began. And the result of that balance was one of the most influential partnerships in planetary history. The moon stabilized Earth's axial tilt. Without it, Earth's tilt would vary wildly over time, swinging between 0 and 85 degrees. With such instability, the planet's climate would be chaotic, violent temperature shifts, erratic seasons, possible collapse of long-term ecosystems. But thanks to the moon's gravitational pull, Earth's tilt remains relatively stable, wobbling gently between about 22 and 24.5 degrees. That tilt will also play a very, very important role in the future. The moon also slows down Earth's rotation. When it first formed, Earth's day may have lasted only 6 hours. The gravitational pull between Earth and the moon has gradually stretched that out to the 24-hour cycle we experience now. This slower rotation helped moderate temperatures between night and day, making the surface environment more hospitable. And then there's the tides. The moon's gravity pulls at our oceans, creating the tides that rise and fall around the world. In Earth's early history, these tides were far more extreme, and they may have played a key role in the origin of life, cycling organic molecules through wet and dry phases along primitive shorelines. None of this was guaranteed. Many planets don't have moons at all. Others have small, insignificant ones. Ours is unique, unusually large relative to the size of the planet with a major gravitational influence. Water is often called the essence of life, but water alone isn't enough. For life to emerge, water needs to stay liquid, stable, and present for billions of years. That's where Earth, once again, beat the odds. After the formation of the moon, Earth was still recovering from a chaotic youth. Volcanoes spewed gas and magma. Meteorites rained down constantly, and the planet's surface was a violent, molten landscape. And yet, not long after all this, perhaps as early as 4.3 billion years ago, the first oceans appeared. The evidence lies in ancient minerals called zircon crystals, which show signs that liquid water existed on the surface of Earth just a few 100 million years after its formation. But how did the water get here? There are two main theories. One suggests that water was present in the rocky material that formed the Earth, locked away in minerals and released slowly through volcanic activity. The other theory proposes that icy comets and water-rich asteroids bombarded the planet after its formation, delivering water during a phase known as the Late Heavy Bombardment. It's likely that both processes played a role. Whatever the source, Earth's water didn't simply appear. It remained. Take Mars for comparison. Mars likely had oceans and rivers billions of years ago, but because of its smaller size and lack of a strong magnetic field, it lost most of its atmosphere to space. Without enough atmospheric pressure, water boiled away or froze solid. Venus, on the other hand, is Earth's near twin in size, but with a completely different fate. Its thick atmosphere created a runaway greenhouse effect, raising surface temperatures to over 450 degrees C, hot enough to melt lead. If Venus had any water, it boiled off long ago. Earth sits in a narrow Goldilocks zone, the region around a star where conditions are just right for liquid water to exist. But even being in the right zone isn't enough. Earth had to retain its atmosphere, regulate its temperature, and avoid the extreme fates of its neighbors. That required several things to go right. A stable climate, aided by the moon's influence and Earth's slow rotation. A protective magnetic field, generated by Earth's spinning metal core, which shields the planet from solar wind that could strip away the atmosphere. A balance of greenhouse gases, particularly carbon dioxide and water vapor, which trap enough heat to keep the planet warm, but not too much to overheat it. And finally, Earth needed time. Billions of years of uninterrupted stability. a planet with active geology, plate tectonics, and a carbon cycle that kept the climate within livable bounds, all while orbiting a star that, by cosmic standards, is unusually quiet and long-lived. Again, not only water appeared, which is already a very rare thing, but it stayed for 4.5 billion years. That's third of the age of the universe. Earth had to be stable. Liquid water for over 4 billion years. Enough time for simple molecules to become complex, and for complexity to spark something more. But what was going on in those waters? Life, as we understand it, is chemistry. But it's not just any chemistry. It's a breathtakingly complex dance of molecules, systems, and self-replication. And somewhere around 3.5 to 4 billion years ago, that dance began on Earth. This moment, when non-living matter became alive, is one of the greatest mysteries in science. We call it abiogenesis, the origin of life from non-living chemical compounds. And despite decades of research, we still don't know exactly how it happened. But we do know this much. It was incredibly unlikely. In the ancient oceans of Earth, conditions were both violent and rich. The atmosphere was thick with volcanic gases, methane, ammonia, carbon dioxide. Lightning flashed across the skies, and hydrothermal vents on the ocean floor spewed mineral-rich water into the depths. These chaotic environments may have been the birthplace of life. One leading idea is that simple organic molecules, carbon-based compounds like amino acids, began to form spontaneously in these extreme conditions. In 1953, the famous Miller-Urey experiment demonstrated that when you simulate early Earth conditions and add electrical sparks, basic organic compounds begin to form on their own. It was the first experimental proof that life's building blocks could arise from non-living chemistry. But amino acids and sugars are just the ingredients. The question is how those ingredients organized into something that could copy itself. The most accepted hypothesis today is the RNA world theory. RNA, a close chemical cousin of DNA, can both carry genetic information and catalyze chemical reactions. In other words, it can store instructions and do things, a combination essential for early life. If random chains of RNA began forming and some were stable enough to persist and copy themselves, however imperfectly, that would be the starting point of evolution. Even that possibility is staggering. A single strand of RNA stable enough to replicate, forming spontaneously in the right place, under the right conditions at the right time. A 1 in a billion chance. But it only had to happen once. From there, natural selection took over. Molecules that could replicate did so. Those that couldn't disappeared. Over time, complexity increased. Lipid molecules may have formed simple membranes, protocell walls, that protected these early replicators from their surroundings. Eventually, this led to the formation of the first true cells, capable of maintaining an internal environment, harvesting energy, and reproducing. In other words, life had begun, and it happened fast. Geological evidence shows that life on Earth may have appeared as soon as 300 to 400 million years after the planet cooled enough to sustain oceans. In cosmic terms, that's a blink of an eye. And yet, it took another 2 billion years for anything more complex than a single cell to emerge. But for nearly 2 billion years, life on Earth remained simple, microscopic, single-celled, and mostly floating in the oceans. But then, something extraordinary happened. One cell swallowed another, and instead of digesting it, the two formed a partnership. That moment changed everything. This was the origin of complex life, and it began with a rare and revolutionary event: endosymbiosis. At some point around 2 billion years ago, a primitive, single-celled organism, most likely an archaea, similar to modern extremophiles, engulfed a smaller, energy-producing bacterium. Normally, that would have been the end of the story. The host would digest the invader and move on. But not this time. The bacterium survived. Not only that, it continued producing energy, now from inside its new host. Over generations, the two organisms became inseparable. The internal bacterium evolved into what we now call the mitochondrion, the powerhouse of the cell. It began providing its host with a massive boost in energy, far more than the cell could produce on its own. In return, the host protected it and supplied raw materials. This one act of symbiosis, one cell merging with another, wasn't just unusual. It was unprecedented, and it was likely incredibly rare. In fact, in the billions of years of Earth's history, it seems to have happened exactly once. The result? A new kind of life, the eukaryotic cell. If that wouldn't happen, life on Earth would be mostly prokaryotic, simple. Unlike bacteria, which are compact and simple, eukaryotic cells have internal compartments that divide up tasks and allow far more complexity. They have a nucleus to store DNA, mitochondria to generate energy, and the cellular machinery to grow, reproduce, and evolve into larger, more sophisticated organisms. Every plant, animal, fungus, and protozoan alive today, including you and me, is built from these cells. Every multicellular organism is made of them. The difference in energy output alone made this leap possible. Mitochondria allow eukaryotic cells to support much larger genomes, process more information, and perform more specialized functions. And it didn't stop there. Later, a second act of endosymbiosis happened in plant ancestors, when early eukaryotic cells absorbed photosynthetic bacteria, which evolved into chloroplasts. That led to the rise of algae, and eventually plants, filling the atmosphere with oxygen and transforming the biosphere. But it all began with that first step. One cell eating another and choosing cooperation over consumption. A moment where evolution didn't just select for survival, but for partnership. It's one of the most critical turning points in the history of life. Because without mitochondria, there would be no large and complex organisms. But that was microscopic life which remained on Earth for billions of years. Bacteria and single-celled organisms dominated the oceans. They still do, but you know what I mean. Even after the rise of eukaryotes, cells with internal complexity, life still lingered in the invisible realm. Then, about 1.6 billion years ago, something new emerged. Cells began to work together. This was the rise of multicellularity, and again, it changed everything. On the surface, it might seem like a small step, but the transition from single-celled to multicellular life was a dramatic leap in biological organization. It meant that, for the first time, life could grow larger, specialize, and build bodies with structure and purpose. Muscles, organs, nervous systems, these were no longer fantasies of evolution. They became inevitable once the right foundation existed. But here's the key. Cells had to give up their independence. In single-celled life, every organism is self-sufficient. It grows, eats, reproduces, and dies on its own. In multicellular life, most cells no longer get to pass on their genes. Only a select few, typically the reproductive cells, have that privilege. The rest exist to support the whole. That kind of cooperation, from an evolutionary standpoint, is incredibly rare. Why would any cell agree to such a thing? The answer lies in genetic identity and communication. When multicellular organisms form from the division of a single cell, as you did, they share the exact same DNA. This eliminates conflict between different cell lineages and allows for cell specialization. Some become skin, others become blood, nerves, bones. These cells don't compete, they coordinate. But specialization requires more than just shared DNA. It needs cell signaling, adhesion, and programmed death. Cells that know when to divide, when to change roles, and when to stop. These mechanisms evolved slowly, and in many cases, independently. Multicellularity didn't arise just once. It likely evolved dozens of times in different branches of life, but only a few of those experiments led to the kind of complex, macroscopic organisms that would one day walk, fly, or think. One of the earliest known multicellular fossils is Grapania, a coiled, tube-shaped organism from over 1.5 billion years ago. Later came simple algae, and by around 600 million years ago, the oceans were filling with soft-bodied multicellular life, some of it resembling the earliest animals. Multicellularity unlocked a whole new level of evolutionary potential. It allowed organisms to grow larger, live longer, and develop intricate relationships with their environment. It also introduced death, not just as an end to individual cells, but as a necessary function in the cycle of growth and repair. This process, known as apoptosis, is part of what allows complex life to exist at all. And from this foundation, life was ready for its next great leap. In order to achieve complex life, cells had to stop competing and start cooperating. They had to build systems of trust and sacrifice. Billions of years of evolution, all leading to a moment where individuality gave way to unity. That moment laid the groundwork for every tree, every animal, every human being. It was life saying, "Together we can do more." Each one of these processes moved very slowly. For billions of years, life existed, but it was simple, mostly microscopic, soft-bodied, and hidden beneath the waves. Then suddenly, in what amounts to a geological blink of an eye, complexity exploded across the oceans. New body plans, new behaviors, predators, prey, everything changed. This was the Cambrian explosion around 541 million years ago. In a span of about 20 to 25 million years, nearly every major group of animals we know today made its debut. Arthropods, mollusks, worms, early vertebrates, creatures with eyes, nervous systems, skeletons, and jaws. It was evolution in overdrive, and it set the stage for everything that would follow. But what caused it? There's no single answer. Instead, it seems the Cambrian explosion was the result of several rare, overlapping conditions, each one improbable, but together forming a perfect evolutionary storm. First, there was oxygen. For most of Earth's history, oxygen was scarce. But cyanobacteria, tiny photosynthetic microbes, had spent billions of years slowly filling the atmosphere with it. By the Cambrian, oxygen levels finally reached a tipping point, high enough to support larger and more energy-hungry organisms. Complex life needs oxygen, not just to survive, but to grow, move, and evolve. Second, there was genetic innovation. During this period, animals evolved new tools for building bodies, most importantly, Hox genes. These are genetic switches that control body structure, where limbs go, how segments form, how organs are arranged. Once life had these building blocks, it could start experimenting with new designs. And it did wildly. Third, there was ecological competition. Before the Cambrian, most organisms were passive, filter feeders or slow grazers. But as body plans diversified, so did behaviors. Some creatures developed armor. Others developed tools for hunting. Eyes became more advanced. Jaws evolved. For the first time, predators emerged, and with them came the evolutionary arms race. Life began to respond to life. We see the results of this explosion in fossil sites like the Burgess Shale in Canada and the Chengjiang biota in China. These deposits reveal stunning detail. Trilobites with segmented exoskeletons, creatures with feather-like gills, early chordates with primitive spinal cords. It was the first time nature started experimenting with real complexity. Structures that hint at what would become fish, insects, even mammals. But here's the deeper truth. The Cambrian explosion wasn't just about evolution speeding up. It was about possibility itself widening. Once energy was abundant, genetics were flexible, and ecosystems became interactive, life broke free from its microscopic constraints. It started building bigger, faster, stranger forms. And not all of them survived. More than 85% of Cambrian species eventually went extinct. But the foundational blueprints they left behind would be used again and again across hundreds of millions of years. And once life gained complexity, it didn't follow a straight line upward. Stumbled, collapsed, and restarted again and again. And strangely enough, those collapses may have been just as important as the progress that came before. Throughout Earth's history, there have been at least 5 major mass extinctions where life was nearly wiped out on a global scale. Entire ecosystems vanished. Dominant species disappeared. But with every destruction came opportunity for survivors to rise, evolve, and fill the empty spaces. In a strange twist of fate, we exist today because others didn't make it. The most famous of these extinctions is the one that ended the age of the dinosaurs. The Cretaceous-Paleogene extinction, 66 million years ago. A 10-kilometer-wide asteroid slammed into what is now the Yucatan Peninsula, unleashing a global catastrophe. Tsunamis, wildfires, and a sky darkened by ash. In just a few years, nearly 75% of all species were gone. including every non-avian dinosaur. But the dinosaurs had ruled the Earth for over 160 million years. Their dominance kept mammals in the shadows, small, nocturnal, and mostly insignificant. When the asteroid struck, it reset the game. Mammals that once scurried underfoot now had open territory, new niches to explore, and less competition. That mass extinction didn't just clear the board, paved the way for us. And this pattern goes even deeper. The Permian-Triassic extinction around 252 million years ago was even worse. An estimated 90 to 95% of all marine species and 70% of land species were wiped out. It's often called the Great Dying. What caused it? Massive volcanic eruptions in the Siberian traps that released enormous amounts of carbon dioxide and other greenhouse gases into the atmosphere. Subsequent global warming that may have increased temperatures by 5 to 10 degrees Celsius, ocean acidification from the absorbed carbon dioxide, widespread oceanic anoxia, oxygen depletion that created vast dead zones, potential release of methane hydrates from the seafloor, which would have further accelerated warming, possible role of sulfur dioxide and other toxic gases from volcanism. And yet, the survivors of that extinction gave rise to the ancestors of birds, dinosaurs, and mammals. These weren't just accidents of destruction. They were filters, reshaping the trajectory of evolution each time. Species that survived mass extinctions weren't always the strongest. They were the most adaptable, the most flexible. And that trait became crucial in the long path toward complex, intelligent life. There's a chilling thought here. If any one of these extinctions hadn't happened, or if they'd happened differently, our evolutionary path could have been erased. If the asteroid had missed Earth by just a few minutes in its orbit, the dinosaurs might still rule today. There would be no humans, no cities, no consciousness asking how we got here. Out of the ashes of extinction, something remarkable emerged: intelligence. But it didn't happen overnight. After the dinosaurs fell, mammals began to fill their place, not just in size and number, but in complexity. Some evolved into large grazers. Others became predators. But a few branches went down a different path entirely, toward brains, problem-solving, and social behavior. And it all began with the primates. Primates appeared tens of millions of years ago in the dense forests of ancient Earth. They were small, tree-dwelling creatures with forward-facing eyes, grasping hands, and high visual acuity. These traits weren't random. They evolved for navigating complex, three-dimensional environments, leaping from branch to branch, judging distances, and using fine motor skills. Over time, these basic survival traits laid the foundation for something greater. As primates adapted to life in the trees, their brains began to grow, not just in size but in function. They developed better memory, more complex problem-solving, and stronger social intelligence. Because when you live in groups, understanding others, alliances, threats, cooperation can mean the difference between life and death. Eventually, one particular group of primates, the great apes, began showing signs of advanced cognition, tool use, communication, emotional depth. And then, around 6 to 7 million years ago, in the forests and grasslands of Africa, something split. A lineage diverged from our common ancestor with chimpanzees. These were the earliest hominins, our direct ancestors. The hominin journey is not a straight line from primitive to advanced. It's a tangled tree, full of dead ends, failed experiments, and lucky breaks. Species like Australopithecus, who walked upright but still climbed trees. Homo habilis, the so-called handyman who made the first known stone tools. Homo erectus, who learned to control fire, travel long distances, and possibly even form early language. But why walk upright in the first place? Bipedalism, walking on two legs, is an unusual and risky adaptation. It's slower than four-legged movement, puts strain on the lower back, and makes childbirth more dangerous. Yet it freed our hands. And with hands came tools. With tools came food. With food came time. Less time chewing raw plants, more time to explore, communicate, and build social bonds. And then came the brain. The human brain is the most energy-hungry organ in the body. It consumes around 20% of our total energy at rest. That's a huge investment, And evolution doesn't give out upgrades unless they provide a serious advantage. But in the case of early humans, it did. Bigger brains meant better cooperation, better planning, the ability to imagine, remember, and teach. These aren't just useful, they're survival skills. One of the key turning points came with the development of complex social behavior. Our ancestors didn't survive alone. They lived in groups, raised their young together, shared knowledge, and formed early cultures. This meant individuals could benefit from the skills of others, creating a system where knowledge wasn't lost when one person died, but passed on and improved over generations. Over time, hominins began shaping their environment, not just reacting to it. They hunted in organized groups. They crafted more sophisticated tools. And perhaps most importantly, they began using symbols, markings, objects, gestures to represent abstract ideas. This was the prelude to language, and with language came something that changed the rules entirely: shared imagination. Language allowed early humans to plan for the future, talk about the past, and build mythologies. It let them cooperate on scales no animal ever had. They could now form tribes, cultures, and eventually civilizations. About 300,000 years ago, Homo sapiens, our species, had fully emerged. But even then, we weren't alone. We shared the planet with Neanderthals, Denisovans, and possibly other unknown human species. Some interbred with us, others vanished, but we somehow endured. But even after the emergence of Homo sapiens, our survival was never assured. We think of humans today as dominant, global, unstoppable. But for most of our history, we teetered on the edge of extinction, small, vulnerable, and confined to a single continent. The Earth was harsh. Climate shifted without warning. Predators lurked. And we weren't alone. Other human species, Neanderthals, Denisovans, and possibly others now lost to time, shared the planet with us. They were strong, adapted, and in many ways just as capable. So what made us different? The answer lies not just in our biology, but in our ability to imagine and cooperate at a scale no species had achieved before. By around 70,000 years ago, something changed in the way Homo sapiens thought. We began creating symbolic art, burying our dead with ritual, and building complex tools. This moment is often called the cognitive revolution, a transformation that wasn't just about intelligence, but about imagination. It allowed us to form shared myths, collective goals, and flexible social structures. While other animals could work in packs or herds, humans began to cooperate in groups of hundreds, even thousands, without direct personal bonds. We became storytellers, and those stories helped us survive. But we were still fragile. Genetic evidence suggests that at one point, our global population may have fallen to just a few thousand individuals. Whether due to environmental catastrophe, volcanic eruption, or climate shifts, we were dangerously close to disappearing. We didn't. We adapted. And then we began to migrate. From Africa, humans spread across the planet. First into the Middle East, then into Europe and Asia. Eventually, we crossed into Australia, possibly by sea, and later into the Americas, braving frozen land bridges and unknown territories. Every migration was a gamble. Every step into the unknown meant new predators, new climates, new diseases. But humans didn't just survive these challenges, we learned from them. As we moved, we met other human species. Neanderthals in Europe and Western Asia, Denisovans in the East. Rather than destroy them outright, we interbred. Today, most people carry a small percentage of Neanderthal or Denisovan DNA. These weren't just competitors, they became part of our story. But eventually, they vanished. One by one, the other human species disappeared. Homo floresiensis, the hobbits of Indonesia. Homo luzonensis in the Philippines. The Neanderthals, the Denisovans. All gone. Only we remained. Why? The truth is, we don't fully know. Maybe we were more adaptable. Maybe we formed tighter social bonds. Maybe our ability to communicate complex ideas gave us the edge. Or maybe, once again, it came down to timing, to luck. What's clear is that Homo sapiens didn't inherit the Earth, we survived it. We crossed deserts, mountains, and oceans. We endured ice ages. We hunted mammoths. We built shelters. We formed languages. We carved stories into stone and bone and memory. And from scattered bands of hunter-gatherers, we began to settle. We learned to farm, domesticate animals, and build villages. Civilization was still far off, but the groundwork had been laid. We had passed through another razor-thin gateway in time, one where extinction loomed on all sides. And yet, through imagination, adaptation, and cooperation, we emerged, not as the only possible outcome, but as the one that happened. From this point on, the story wouldn't just be biological, it would be cultural. Evolution had taken us as far as it could. The next chapter would be one we wrote ourselves. Roughly 12,000 years ago, everything changed again, not through genes or anatomy, but through something new: culture, memory, and civilization. For most of our history, humans lived as hunter-gatherers. We moved with the seasons, followed herds, foraged for food, and lived in small, tight-knit groups. Life was physically demanding, but it was also balanced. We understood the land, and the land sustained us. For tens of thousands of years, this was the rhythm of human life. Then came a turning point so profound that it reshaped the destiny of our species: the agricultural revolution. Somewhere in the Fertile Crescent, an arc of land stretching through parts of modern-day Iraq, Syria, and Turkey, humans began to domesticate plants and animals. Wheat, barley, lentils, goats, sheep. This wasn't a sudden shift. It took generations, but eventually, people began staying in one place. They planted, they harvested, they stored food. And in doing so, they created something our species had never had before: surplus. That surplus changed everything. With more food than a single family needed, humans could support individuals who didn't hunt or farm: toolmakers, builders, spiritual leaders, early scientists. Villages turned into towns. Towns grew into cities. Labor became specialized. Hierarchies formed. And with settlement came permanence. Homes, granaries, temples, walls. This wasn't just a shift in lifestyle, it was the birth of civilization. And yet, it was a double-edged sword. Agriculture allowed for population growth, but it also introduced new vulnerabilities. Dependency on a few crops meant that famine was never far away. Living in close quarters brought disease. Hierarchies created inequality, and with stored wealth came conflict. Human societies became larger, but also more fragile, more complex, and sometimes more brutal. But they also became capable of something remarkable: shared knowledge. With writing came history. With trade came ideas. Humans began recording what they knew, passing it not just orally, but in permanent form. They built monuments, developed mathematics, studied the stars, and mapped the seasons. For the first time, we could accumulate knowledge across generations and accelerate the pace of discovery. From Mesopotamia to Egypt, from the Indus Valley to the Yangtze River, great civilizations rose, driven by agriculture, coordinated labor, and belief in something larger than the individual. These were no longer scattered tribes. They were organized, powerful, and interconnected. And all of it, every temple, every law, every innovation, grew from the improbable series of events that came before. A universe fine-tuned for complexity. Planet with liquid water. A cell that took in a mitochondrion. A chain of survival through mass extinctions. The rise of language, cooperation, and imagination. The fragile endurance of our species through bottlenecks and migrations. The agricultural revolution was not guaranteed. In fact, it likely happened independently in several parts of the world, not just in the Middle East, but in China, Mesoamerica, and the Andes. Each time, it depended on the right combination of plants, animals, climate, and human insight. Another one in a billion moment, repeating itself just enough to change the world. And now, for the first time in the long history of life, a species had the tools to reshape the Earth, not just to survive, but to control its future.